Hi everyone. We start with our article title. It's a perceptual structure and patterns modeling of aftershock-induced landslides. So if there is any questions or suggestions regarding to the manuscripts or any other issues, please do not hesitate to contact me. I added all the contacts at the end of the slides. My emails, also my connection channels on YouTube and the Udemy courses. I will start with the introduction, then discuss the study area with the methodology that followed and talk about results and the discussion, then we conclude the work. The earthquake happened on the 25th of April, actually, that struck the Park and the central Nepal, the magnitude of 7.8, and also the aftershock, which is in the 12th of May, which is almost the 7.3, that triggered landslides, rockfall, and almost 25,000 incidents within 90 square meter, which caused too much losses in the land uses, and also the block the road and dam the river and so on. So what today we are going to do, we will try to produce a prediction map about the study area, but with the contribution of the method of selecting the training and testing data for the modeling, for producing the model of producing the prediction map, which is it's one of the crucial actually step, because the training data, it's represent the dependent factor, which is most of the machine learning, like the artificial intelligence, like regression, clustering, the supervised, unsupervised, the cluster techniques, which is depend on. So usually the data or the incidents that it represent the inventory, it's collected by many means, actually by the satellites images or the field work we use to process it, and we classify it in the training and testing data. Training, we will use it to run the model, and testing and validation, we use it to test the accuracy of the model output. So here in this study, we noticed that all the incidents that caused by earthquake and other aftershocks are clustered near or around the epicenters. That's take as a hypothesis that most of the events happen in the study area, they follow the cluster matter, or they are the cluster distribution pattern around the epicenters. So logically, following the classical style, that choosing randomly from the training data, it won't be the most correct thing to do here. So we tested the hypothesis about the future events. Even if it's happened, it will happen also around the epicenters in the cluster manner. So that makes sense that our training data need to be chosen from the clustered events, not randomly. So we will discuss about this later in the methodology. So here we investigated two methods, which is unsupervised methods, with the k-means and the expectation-maximization, that using the Gaussian mixture model. Both functions actually run within our programming environment, and the machine learning function here, algorithm, we use the generalized linear model, the regression method, which is the well-known and actually well-proved, actually one of the well-proved methods in the literature. Also, we keep the normal and the classical the classical sampling technique, which is the random, that usually to be like 70 to 30%. We kept it as well to test the hypothesis with this classical method. So quickly, we'll talk about the study area. I think need to turn my screen now here to give more space. The study area actually it's in the southern part of the Raswan district, north of the Kathmandu Valley. As we said that we collected the events after the 2 dates of the 25th of April and 12th of May, with actually the big force acceleration found actually in the study area is around 0.5 to 0.8 g force, which is in this scenario actually the landslide density have no direct correlation with the BGA. So, but however, this correlate with the several factors like the slope, and that is also take us that we to see the land cover that is mainly represented by the forest and cultivated lands, and also some water bodies and barren lands. And we have one river here. It's the Trishuli at the main drainage of the area. That, and you can see too many landslides there along the valley on the both side of the river. Here we notice that the most affected areas, as in the in here you can see it's the 3 areas ABC here mentioned in the map and the photos on the right sides. Also you can see the highway, which is we witnessed some landslide actually nearby, while the main events happen around near to the actually the river. You can see here the valley. So the study area is connected to the Kathmandu capital city, actually about this highway, so it might bring also some risk due to the human lives actually if these events do not controlled. Also we have significant damages actually at the earthworks and also the penstock pipe and the powerhouse of the hydropower project at that area, so that we understand that the landslides really as a really disastrous natural hazard in that study area and need to be focused on. In the methodology section, in the methodology we have to investigate firstly the landslides as the dependent factor and the thematic maps which represent the independent factors. So the data collected actually from the Department of the Mines and Geology, as well as topographic maps, which now after we cleaned the data we got to have almost 680 landslide event and landslide location in the database, which also it's prepared using the data from the National Seismological Center, Google Earth, and also high resolution satellite image export, and also and the BGA taken from the USGS website. We started by taking the landslide data and the inventory, and we used the k-means first to find the we took 70% of the data. Okay, we took it randomly, 70% randomly first. Then within this 70%, sorry, yeah. So we started with the k-means, and we choose 70% of the data based on the clustered, not randomly. We use 70% of the data that clusters, and we keep the 30% side, that this 30% it was used later for testing the susceptibility map. Same as we did with the Gaussian mixture model. Also we did the same. First we found the clustered, the number of the clustered, and then we get to find the clustered region, and based on this clustered region we keep the 30% of the points, and we just collected the clustered regions. And also additionally we followed the the classical style, also we choose 70% of the study area randomly without any assumption about cluster or whatever. So we just choose 70% of this 680 location to train the model, and we hide the 30%. So here in short about the unsupervised methods. So as you see here, what the k-means, which is unsupervised methods, depend on the k numbers. So you need to find the k number, how many cluster you need to take. So in here actually the number of the clusters used to have the centroid, you can see this, the three groups here. Okay, when we give the number of k-means as a 3, it will show us where is the best center, and this after the center it will try to collect the data around the 3 centers, the most denser centers to choose from. Okay. Worth to mention that in the k-means, to determine the number of clusters actually is still it's still not clear in some literature. That still have the manual assumption, but here we use the elbow method. The elbow method that proposed to us which is the best number of clusters need to be taken in this method. So we provided the k-means with the elbow method to find the number of clusters. So when we come to the expectation maximizing algorithm for the Gaussian model, so we have like, it's considered to be like the soft version of the k-means, which is the enhanced version. Okay. Here also it's assumed that also it depends on the 3 parameters actually. First it will take the mean, also the covariance matrix, and the associated probability in the mixture. So you have 3 parameters within the expectation maximizing algorithm. Also the mclust function that it was used in the R environment. So worth to mention also that using the expectation maximization GAMM, in order to find the number of clusters, actually here we are using the what's so-called the Bayesian information criteria, that is determined based on different models using the covariance matrix. Based on this method, we will determine also the best fit or the best number of clusters for the expectation maximization. Moreover, we have the logistic regression method algorithm actually, which is the well-known here, which is the actually taking the relationship between the dependent and independent variables and estimate the probability that occur by applying the maximum likelihood estimation after transforming the dependent logit into dependent variable into logit variable 0 and 1, and using the 2 equations here, the probability also as well as the linear model for the intercepts for the logistic model, which is giving the weight, the B representing the intercept and the X represent the independent variable. So we come to the results and discussions. Firstly, we start with the k-means. As you see here, the k-means it's using the optimum number of clusters that obtained from the elbow method. For the finding, they analyze the total within the cluster sum of squares. So this is the function, find the number of clusters, and whenever there is a band, actually indicate that the additional clusters beyond it, it's significant and doesn't improve the total cluster sum of squares. So whenever we reach to the elbow method, that's why it's called the elbow. Whenever we find the band, that's mean this is now we start to fix here, and we use this number of clusters, because the following number of clusters more, it won't improve the model. Okay, so here based on the band, actually we found around 7 clusters. So more than this, actually this will just add complexity. So if you see here on the right side, and we have the 7 clusters. In every cluster we have the number of events. So you can see here, for example, in the first cluster we have 115, and in the fourth one we have 60, and so on. On the left side you can see here, this is our event tree, and this is the groups or the clusters. So I can see based on the colors here, now we have 7 colors. Every color indicate to or refer to one cluster. Yeah, so as you see here now in the GMM, we have to use the BIC, as you said. The BIC for this variables, it shows us 14 available model parameterization that obtained. Okay, so in the BIC, the higher is the value, is the better for the model. So you can see here on the right side, the model with the number 7. You can see here one of the parameters, which is the triple V. It's coming as a value of 7. It's coming on the cluster of 7. Also, we have the others, like the EVV here. This is the acronym of it. It's come out around 9, and the EVE around 8. So as you see here, all the values coming from 7 to 8. So we assume that taking the number 7, Y is also then to use it to compare it with the previous k-means. We can take the number of 9, but number 7, because already we took 7 earlier, and also we have one indicator here, which is the triple V, which is the highest. So also it's recommended to take the highest value. So as you see here now, the one additional result is coming from the GMM, which is the uncertainty. The Gaussian distribution, actually, the measure of the uncertainty for the associated with the GMM classification obtained here, and as you see that there is some landslides happen within the swath. So there where we can see there's some uncertainty with the clusters for the GMM. So the point that couldn't fit into any of the 7 clusters considered to be uncertain. Okay, and it's shown here. You can see that the points that it's out of the center of the cluster, that it doesn't fit. So that have almost occurred within the swath zone between the largest shock and the smallest, the aftershock as well. Finally, also after that, when we run the model, we have the ANOVA test. It will guide us to the to analyze the similar analysis of the variance. So the smaller variance in the conditioning factor reflect the higher likelihood in the occurrence of the landslide. That's why we use the ANOVA here to give us additional guidance within the logistic regression model. So in terms of the factors importance, as you see here with the colors, always the slope, it's the highest actually, because all of this area have been with the slopey area, so you can see the slope also affect too much in the analysis, followed by the SPI and the TWI. And why is that? Because the SPI and TWI, stream power index and the topographic wetness index, both of them related to the drain. And also we can see that the banks around the valley of the river there, most of the landslide accumulated around the valley, the river itself. So the area with the low TWI value suffered from more landslide due to the earthquake, and the low value of TWI indicate lower order drainage that increase the instability. Slope and elevation stand out the most influence factor, as we said. SPI, other than in the EM cluster, is an influencing factor. As you said, the Trishuli River, there's a major river there. It's the reason for the instability of the slope during the intensive shaking. Roughness show its influence of landslide, but in the K-means, while TW and curvature aspect are less significant for all the used clusters. Just turn off this one. Yep. Moreover, we showed here the accuracy for the kappa index used for the expectation maximization, which makes better model for the high kappa index. Also, it shows in the kappa, it was not too much clear, but it's a slight different in the EM model. It shows a little bit higher than the K-means. For the accuracy, also we can see there is a small improvement with using the EM rather than the K-means. So the study area was dominated by the lesser Himalayan rock, and the observation show that the high concentration of landslide in the slopes composed of the metamorphic rocks actually of the lesser Himalaya sequence. Comparatively, a few landslides occur in the moderate slope, and most of them were confined in the influence of the steep slopes, and which supported by the literature as well. So we could notice here that using the ROC curve results, there is not much difference actually between the using the expectation maximization and the K-means. Is almost close to each other, but it shows definitely better than using the normal sampling style, while using the kappa index and the ANOVA and the variance and the stability. Actually, the stability of the models, the EM was more stable than the K-means, even in terms of finding the uncertainty, also testing the PIC for the clusters themselves. So that in this case we propose to have used the expectation maximization. So to sum up, that this research mainly focus on the finding the pattern of the landslides that it happened after the landslide, after the earthquakes, and also after the aftershock in the study area for the north of the Kathmandu Valley in Nepal. Here on the right side you can see the susceptibility map, within the red, dark red is the most susceptible, which is, you can see here, most of the valleys area, they're all susceptible because of the landslides. At the same time, we predicted some areas that it doesn't have an inventory over there. Second, the novelty of the sampling strategy here, using the cluster of the incidents rather than using the random distribution selection. So we can't just avoid the nature of the landslide incidents. We need to test, we need to study the nature of those events, how it happened, how they are distributed. Based on this nature, we determine the training, because the model is garbage in, garbage out. If you feed it with the just random locations, it will also work on this random itself. So this incidents actually we tested, we investigated that it was clustered in the beginning around the epicenter. So definitely in the future it will be around those centers. Also, we found that the significance of the EM over the K-means, and as well as all the conditioning factors contribute to the landslide in the study area, but the stream power index and the TWI were the most significant in this study. So for the future work, we propose to use the current finding with verifying it with using different clustered methods. Okay, there is the K-medians. There are too many cluster methods out there, need to be tested to see which it can enhance the current findings, and also to prove the hypothesis of using the clusters of the incidents instead of using the random pattern distribution. So we would like in the end to thank the Department of Mines and Geology in Nepal to making the geological data available. So thank you for your attention. This is again Omar Al-Tuwaini. Please, if you have any questions, here my email is about the SCADEC@outlook.com.